we left off yesterday looking at question number 3. We didn't get a chance to go through it together, so that's where we're going to start. Okay? So this has to do again with work energy theorem, kinetic and potential energy. This one mostly with potential energy. Okay? So we have a winch that's pulling a 250 kilogram block up a 20 meter long inclined plane. Okay, so this is 20 meters. There's a block on it that's 250 kilograms. Okay, the angle is 35 degrees. Okay, and we are looking for what's the change in the gravitational potential energy that the block undergoes. All right, so it doesn't mention anything about acceleration here, so we can assume that all the work being done is changing what? Just potential energy. Okay, that's why it's going up the ramp. All right, that means that down here, the potential energy is 0, and up here it's something else. Okay, we can't calculate that yet because we don't know what the final height is. Right? If we're going to find that final height, then we have to figure, if we're going to find out the final potential energy, we've got to find the final height. Can we do that? Yeah, it's the same trick that you used on the quiz if you outsmarted the quiz today. Okay, they gave you the hypotenuse as well as the angle, so you can calculate that opposite side. All right, so the sine of 35 degrees equals the final height, the opposite side, divided by the hypotenuse, 20 meters. So I'm just going to multiply both sides by 20 meters, and that'll give me my final height. So I'll have sine of 35 times 20. Okay, so 11.47 meters. All right, now that I have that, now I can look at this from a work energy theorem perspective. Okay, work is changing the potential energy of the box. Okay, that's going to mean m times g times h final, my final potential energy, minus my initial potential energy, which, since I start at the bottom of the ramp, is 0. Okay, so calculate the work. All I have to do is go 250 times 9.81 times 11.47 meters. Okay, and that should give us our 2.81 times 10 to the 4 joules. Okay, really we just have to recognize what kind of energy is changing, set up work energy theorem to calculate it. I will tell you that on your unit exam, I have made it so that the energy questions only involve changes in one kind. Unless I change my mind, then I'll tell you. Okay, but for right now, it's one of each kind. And one potential, one kinetic. Okay, questions on that one? Then, let's talk about kinetic energy, because yesterday all we got to do was potential energy. So, something has kinetic energy if it's doing what? Moving. Okay, if it's moving, then it has kinetic energy. Okay, what are the things that kinetic energy depends on? Yeah, speed, how fast the object's going, and what else? Nope, not gravity. Okay, picture this situation. You are standing in the street for some reason, and a dump truck is coming at you at 30 kilometers an hour, and a kid on a tricycle is coming at you at 30 kilometers an hour somehow. Big situation. Okay? Which one should you step in front of? The truck. Why? Not the truck. Please, not the truck. Huh? The kid. Why? He weighs less. Yeah, well, has less mass, also weighs less, but yeah, technically has less mass. Okay, the two things that velocity depends on are the mass of the object and how fast it's going. Okay, it's possible for that kid to have the same amount of kinetic energy as the dump truck. He just has to go really fast. Okay, I mean, speed, remember, has an exponential relationship with kinetic energy. So, if he was to go, I don't know, maybe 10 times faster, then it might make up for the lack of mass or the difference in mass between him and the dump truck. Okay? It doesn't take long. Right? This is the principle behind a lot of the kind of weapons research that's been going on. I don't know if anyone's ever heard of a railgun. Yeah. Okay, so a railgun is a kinetic energy weapon. It's not explosive. Okay, Okay? There's no high explosive involved in firing a projectile with a railgun. Okay? What a railgun does is it's got a bunch of magnets, essentially, and the magnets propel just a slug, okay? A big metal slug, okay? They propel it to unbelievable speeds, okay? And it does damage strictly on its kinetic energy. It can rip through the armor of another ship, okay? Simply because it's going so fast. It doesn't need to blow up. Okay? It's just got so much speed, so much kinetic energy that it can do damage because of that. Right? The idea behind this is it's good if you don't have to carry a bunch of high explosive on a boat that might be shot at. Okay? What usually sinks warships is their own ammunition blowing up inside. Okay? So you don't want that, okay, obviously. So the idea of a railgun is something that you can use to shoot at other people, but that won't blow up on you. So the same idea, okay, goes into all things. Okay, if something's moving very fast, okay, then it can have a lot of kinetic energy, even if it doesn't have a lot of mass. All right. This is also kind of true for light. Okay, light is made of like tiny, essentially massless particles called photons, but they're going the speed of light, so they can impart a great deal of energy. Okay, we use that in solar panels, we use it in X-rays and all kinds of other things. Okay, we harness the fact that things can have a lot of kinetic energy by simply their spin. All right. So yeah, kinetic energy is dependent on mass and speed, but remember that speed is exponentially related to this. Okay, mass is linearly related. So if I double the mass, I'll have twice as much kinetic energy. Okay? If I double the speed, I'll have 4 times as much. Okay, so on a highway, a car has a mass of 1,200 kilograms traveling at 20 meters per second. It has the same kinetic energy as a loaded van whose mass is 4 times the mass of the car. Okay? What is the speed of the van? Okay, the key part of this is that their energies are equal. Okay, it says that in the question. It has the same kinetic energy, okay, as the loaded van. So I can start this out by saying the kinetic energy of the van is equal to the kinetic energy of the car. Okay, so I just put in V for van and C for car. All right, I want to figure out the speed of the van. So what do I have to move? Yeah, I got to take the 1/2 mass of the van, okay, over to here. Oh, yeah, mass of the van. I put too many V's there. Mass of the van. All right, so I've got that. That's gone there. That gives me the speed of the van squared. I just want the speed of the van. All right, so that's going to be 1/2 times 1,200 times 20 squared, okay, divided by 1/2 times 4,800. All right, now, what would common sense say the speed of the van is before I calculate it? It has 4 times the mass, so it must be going faster or slower. Is the van going faster or slower than the car? If the van is heavier, slower. Yeah. Okay. Remember, mass affects your kinetic energy as well. Their kinetic energies are equal, and the van's 4 times heavier, so the van is going slower. How much slower? Remember, speed's exponentially related. Nope, not 8 times. 1/2 as fast. Okay, let's calculate it. Let's just make sure. Okay. 10 meters per second, half as fast as the car. Okay? If they had the same mass, okay, they'd obviously be going the same speed, right? But they have the same amount of energy and the van's 4 times heavier. That means it has to be going half as fast because speed is exponentially related. It's got 4 times the mass, so it must be going half as fast. Okay, I want you guys to try. So these all just use this. Okay, they're all just kinetic energy questions. Okay, number 3 involves a change in kinetic energy, so I want you to do that. Because the other ones are just, can you manipulate 1/2 mv squared? I already know you can do that. Okay, so let's try number 3. Okay, so on number 3, we have this skateboarder. We know their mass is 65 kilograms, and they increase their speed from 1.75 to 4.20 meters per second as they roll down a ramp. Now, obviously, if they're rolling down a ramp, there's also a change in what? In potential. But all that change in potential is actually becoming kinetic. Okay, in a perfect physical world, that's what happens. So we don't have to worry about calculating the change in potential. It's the same as the change in kinetic because they're converting into each other. All right, so all we have to do is say, all right, the change in kinetic energy is going to be 1/2 mvf squared minus 1/2 mvi squared. Final minus initial, and that's how we calculate the change in anything. Okay, so I just have to plug in my numbers. 1/2 times 65 times 4.2 squared minus 1/2 times 65 times 1.75 squared. Okay, and when we do that, we should get 474 joules as our change in kinetic energy. Are they all right with that? So, in a multiple choice item, could you be asked something like what we were talking about before, which is, like, what are some factors that could affect the kinetic energy of an object? Is that something that could be gained for multiple choice? Absolutely. Okay, those are like kind of checking, fact checking, or checking your understanding a little bit without having to do any math. Okay, so as long as we understand that. All right, I would like you guys to try both of these. Okay, they both have to do with kinetic energy. Okay, the second one has to do with making a big crater. Okay, the energy of meteors.
Almost like a nuclear reactor.
Yeah, almost, except without the radioactive side effects. All right, give those ones a try. Okay, can you do number 2 without doing any math? You can. Okay, so there's kind of a quick way to do it. Certainly you could do it with math and verify, okay? But there's quicker ways to do it because it doesn't actually ask for any numbers as an answer. It just asks which would be more effective at damaging a fortification, okay? Because way back in the day, that's how they wrecked stuff, okay? They had cannons. You put a whole bunch of gunpowder in the cannon, you put a big metal ball in front of the gunpowder, and you detonated the gunpowder. You lit the fuse and walked away, okay? And then you lobbed these big giant balls at the enemy's castle, okay, or whatever, okay? And the more times you hit it, eventually it would crumble, okay? So, which would be better? A 1.5 kilogram ball moving at 550 meters per second, or another cannon that fires cannonballs that are 1/3 of the mass, but twice the muzzle velocity. Okay, if they have 1/3 the mass, and they're moving the same speed, they'll have 3 times less energy, agreed? All right, but they're moving twice as fast, which gives them 4 times as much energy. So we divide it by 3, then multiply by 4. Are we still getting bigger? Yep, 4/3. Okay, that's bigger than 1. Agreed? Okay, so it's just a matter of looking at those factors and not actually bothering to calculate. Could I figure out all that stuff, calculate all those numbers? Absolutely, but I come up with the same answer. Okay, faster is better, okay, in this case. All right, for number 3, hopefully you're working on that one right now. Okay, they talk about this this meteor that hit in Arizona and made meteor crater, which is what that picture is over there. Okay, the meteor had a radius of 40 meters and its mass was 2.6 times 10 to the 8 kilograms, and it struck the Earth at a speed of 72,000 kilometers per hour. Now, what do we need the speed to be in? Meters per second. So make sure you do that conversion first, okay, and then go from there, and then we'll talk about the whole tons of TNT thing, okay, which is how they measure explosive potential. Okay, so for part A of the meteor question, okay, this is what we know. We know that the mass of the meteor is 2.6 times 10 to the 8 kilograms, and we're going to need that. We know the speed is 7.2 times 10 to the 4 kilometers per hour. Okay, so that's going to be 72,000. Okay, I don't know why I put that in brackets. Divided by 3.6. Okay, is 20,000. Okay, so 20,000 meters per second. That's really fast. Okay, and we're looking for the kinetic energy at the instant of impact. So EK will equal 1/2 times 2.6 times 10 to the 8 times 20,000 squared. Okay, I'm getting times 10 to the 16.
I got it.
Oh, okay. All right, so 5.2 times 10 to the 16 joules. All right, so that's a lot of energy. But when we look at a number like that, it's kind of hard to put it into perspective, okay, how many joules and how much energy that is. Okay, so the fine people who brought us nuclear weapons came up with, okay, a way to measure the destructive potential of any explosive device or basically any other like impactor like this, okay, like a meteor hitting the Earth. All right, they said, we're going to tell you how many tons of TNT that impact or explosion will be equivalent to, because they knew how many joules of energy a ton of TNT would release if it was blown up. All right, so when 1 ton of TNT explodes, 4.6 times 10 to the 9 joules of energy is released. Okay, so if we're looking at this number here for the amount of joules that we got, and we divide those two, that'll tell us how many tons of TNT this impact was equivalent to. Right? So I'm going to take that number that I have, okay, and I'm going to divide it by 4.6 times 10 to the 9 tons of TNT, joules per ton. All right. Okay, is that a lot? Yeah, it is. It's kind of a lot. Okay, I mean we're looking at what, 11,304,347 tons of TNT. That is 11 megatons of TNT. To give you perspective, the Hiroshima bomb was 1 kiloton. So the bomb they dropped on Hiroshima was the equivalent of 1,000 tons of TNT. Okay? This is 11 million tons of TNT, slightly larger. Okay? Now, modern nuclear weapons are, unfortunately, their yield is measured in megatons. Okay? Modern nuclear weapons will release the energy equivalent of several million tons of dynamite. Okay? Which, you know, you get a nuclear weapon, they're still big and they're still heavy, but they're a lot easier to move around than 11 million tons of dynamite. It's also a lot easier to manufacture than 11 million tons of dynamite. Okay? It's hard to get that much dynamite in one place. Okay. Now, I'm not saying that you should use nuclear weapons, because that's obviously very bad. Okay? But they are very powerful and thus scary. Okay? That they could, what's that? Well, it left a big crater. I mean, that crater is, what did they say? It's like, it's a couple of miles across, I think, that crater. It's big. I mean, it's small in terms of craters. Like, if you look at the crater that was caused by the Chicxulub impact, the one that killed the dinosaurs, like, that's like part of the Gulf of Mexico. Really big. Okay, that impact obviously had some pretty major effects on all life on Earth. It was much bigger. That one was, who knows how many billion tons of TNT. Okay, would be in an impact like that. Okay, so this, yeah, like we look at that and go, oh, that's a crater. You know, it's not huge, it's big, but yeah, if you were to do that with a nuclear bomb, you could get a big crater too. Okay, now the thing with nuclear bombs, and this is kind of even scarier about them, is they don't detonate when they hit the ground. They detonate in the air above the ground. That way their explosive potential spreads out better. There's people out there that think of this stuff. That's really, there's people out there that come up with that kind of stuff. Okay? That's the really scary part. That way, instead of making a big hole in the ground and damaging the ground, the damage spreads out over the ground. Okay? Instead of, making a hole. Yeah. Scary stuff. There, you can rock yourself to sleep tonight with that thought. Okay, yeah, and there's a lot, yes. Enough to destroy the world many times over. Yeah.
I watched a video.
Well, yeah, and it's what they call it, right? You learn it's in social, mutually assured destruction, MAD. It's like the most appropriate acronym ever, okay? We have to have lots of nuclear weapons because they have lots of nuclear weapons. And we have to know that if either one of us shoots one, we'll destroy the whole world many times over. Mutually assured destruction. Nobody gets to win. That's the, what they call it, deterrence. Deterrence on that, yeah. Yeah, everybody loses. Yeah, there are no winners in nuclear war. Okay, so for these ones here, oh no, we've done a few like that already. Okay, and we did. All right, I want you guys to try that one. It's a little bit different. Okay, it's still a change in energy question, but you have to do a little tiny bit of force stuff in it. So, it just wants us to know what is the potential energy of the object when it's at the top of the incline with respect to the bottom. I don't even need any of the stuff that came before that except the mass. Okay, I don't need to know about that force that was used and applied. Don't need it. Okay, I just want to calculate the potential energy at the top. Well, the potential energy at the top is m times g times h. Okay, all I have to do is go 200 times 9.81 times 6 meters, which gives me 11,772, okay, which obviously rounds up to 1.2 times 10 to the 4 joules. Okay, if I do this with forces, it's way more involved. I got to calculate F parallel. I have that applied force. That'll get me the force of friction because part of the applied force is overcoming the force of friction, okay? And it's a mess, right? I don't want to have to do it that way because it takes way, way longer to arrive at the same answer, okay? In this case, it just asked, what's the potential energy at the top? Well, let's do it the easy way. I have the height, I have the mass, I have gravity. Let's just do it that way. Okay? Now, with a ramp, okay, the inclined plane is like the simplest machine. Okay? And it is a machine, we call it a machine anyway, because it makes work easier. Does it make less work? It does not. Okay? It doesn't matter which way I get this box to the top of this ramp. It will require the same amount of work. Okay? And this goes back to the definition of work. What's the definition of work? Change in mechanical energy. All right, so if I push this box up the ramp, okay, and get it to here, it'll have this much energy. If I pull the box up the ramp to that height, it'll have this much energy. If I lift it directly to the top, without using the ramp at all, it'll have how much energy? Same amount. All right? What's different is to lift it here, I have to use more force over a smaller distance. The purpose of a ramp is to allow you to do the same amount of work using less force. Okay? It makes work easier, but you have to use that less force over a greater distance. Okay? And that's the whole idea behind a ramp. I can use less force because the ramp supports part of the weight that I'm moving. Okay? So I don't have to use as much force to push it. I don't have to lift it directly. Okay? That's how the Egyptians built the pyramids. Okay? They used lots of ramps, okay? Really long ramps that wound around the pyramid, okay, in order to get the blocks to the top. Okay? Inclined planes mean that you can use less force over greater distances. Okay? And then you don't have to lift giant rocks with Stone Age tools, because that would have been very, very difficult / impossible. Okay? All right. Those are all really, really easy. Sorry, I'm skipping the ones that are beneath you. Okay. Oh, I skipped them all. Oops. Okay. I actually want to talk a bit about conservation of energy, but I'll give you like a 3-minute break here just to get up and move around a little bit. Okay, and we're going to talk about conservation of energy. All right, so we're going to look at conservation of mechanical energy. And this is something you did back in Science 10, but it was probably during the learning from home, or as we like to call it, being at home. Not a lot of learning took place. Okay, so it probably took place for you during that part. So you may or may not remember it, or it may be a bit fuzzy for you, and that's fine. Okay, because we don't actually need to build on anything that you learned last year. We're just going over exactly the same thing. All right, so if you didn't get it last year, well, you're going to get it again. Right? It doesn't get any harder than what you did. Okay, so the first thing we have to understand is something that we learned in Science 10 physics. Energy cannot be created. It cannot be destroyed. Okay, it can look that way sometimes. But what's really going on when it looks like energy is being created or destroyed is that it's being transferred or converted from one form to another, or transferred from one object to another. Okay? So when something, like let's say, slides down a ramp, so a kid's on a slide in the playground, they slide down the slide, okay? They don't have the same amount of energy at the bottom of the slide as they have at the top in the real world. Okay? And it makes it look like energy is being destroyed, but what's really happening to it is it's being changed. Okay? It's becoming heat and sound and other forms of energy that don't count when they get to the bottom. Okay? Like they're going slower than they should be because they've lost some energy along the length of the slide. Okay? But in real world, even in the real world, energy is conserved. It just doesn't all turn into what we expect. We don't deal with very many problems where energy is not fully conserved. We work in kind of the perfect physical world where when a roller coaster goes down a track, okay, it doesn't lose any energy along the way, which would be a very scary roller coaster because it would make no sound whatsoever. Okay, except the screaming people, but okay, that doesn't count. So energy can't be created, can't be destroyed. Energy can be converted from one form to another, okay? And then obviously use this idea, okay, of the law of conservation of energy to calculate other variables like the speed or the height of an object as it's moving through a path, okay? So there's two kinds of energy, kinetic and potential. We've been talking about that. And the sum of an object's kinetic energy and potential energy is its total mechanical energy. That's kind of the most important part, okay, of the law of conservation of energy. That the total mechanical energy initial and the total mechanical energy final are equal. The amount of kinetic and potential, however, will vary. Okay? But when you add them together, they're still going to be equal on both sides. Okay? So as a roller coaster goes down a track, like we see in the picture here, at the beginning, most of their energy is potential, very little of it is kinetic. Okay, at the end, most of it is kinetic, very little of it is potential, but the number, the total number, is still the same. Everybody okay with that? All right, so what we see here, okay, is something like this. If there's work done, then there's a change in energy. And that's what we've been working on up until right now, okay? If work happens, then energy changes. Final and initial aren't equal. But what we're going to be looking at now are perfect physical world situations where the initial and final energies are equal because no work is being done. Okay? No mechanical energy is being transferred out of the system. Okay? All right. So, in other words, the final mechanical energy in a conservation of energy problem is going to be equal to the initial, okay? So the total mechanical energy remains constant along the path between the initial and final points, okay? So, as this thing is going down this ramp here, it's turning its potential into kinetic. Okay, so here would be like the maximum potential and the minimum kinetic. Down here would be the maximum kinetic and the minimum potential. Okay, what about right here? Some of each? Yeah, some of each. It's hard to say which. Probably a little more potential than kinetic. It's about, it looks like a little more than halfway. Okay, here though, okay, there definitely be more kinetic than potential because we're closer to the bottom. All right, obviously here we're back in the same situation as back here. Okay, here there'd be more kinetic than potential and so on. So as long as there's some height above the bottom, there's some potential. Okay, if you're at the highest point, then there's essentially all potential and no kinetic. Okay, everybody okay with that? Now, how many of you have ridden a roller coaster? All right. Okay, so you've had this experience then. Most traditional roller coasters rely on a trolley that is essentially towed to the top of the hill. Okay, that's how it gets its mechanical energy. The trolley, okay, the conveyor belt moves the trolley to the top. Okay, so that's where all the energy comes from, is from that conveyor that pulls you to the top. When you're at the top, how fast are you going? Pretty slow, right? Like just barely moving. Okay, and then you go over the first hill. Okay, on traditional roller coaster, the first hill is always the biggest one. Okay, because that's where you're the highest. And then after that, you go through loops, around sharp corners, and whatever else. But the first one's always kind of a big drop. Okay, because that's when you have the most energy. Okay, that's when it's the most exciting. They can't save the big drop for the end because the roller coaster in the real world is doing what all the time? Losing energy. Okay? Have you ever stood next to a roller coaster? Besides the people screaming, they're really loud. Okay? Is sound a form of energy? It's because they're really loud because they're losing a lot of energy. There's a lot of friction, okay, in a roller coaster because, for safety reasons, a roller coaster cart has wheels on both sides of the track. Okay, the track is usually a pipe, and then there's wheels on both sides clamped down like this so that the cart can't fly off the track. Okay, if that fails, the cart flies off the track. All bad. Okay, that happened at West Edmonton Mall shortly after they built the Mindbender. Okay, how many of you have ridden the Mindbender? Rode the Mindbender. Okay, so the Mindbender is a very high G roller coaster. Compared to other roller coasters, it's actually not that fast. Okay, it feels really fast, but it feels fast because it's tight. The corners are really, really tight, so you build up a lot of G-forces. An outside roller coaster, they can make bigger because space isn't an issue. Okay, but in the tight confines of an indoor amusement park, okay, you have to have tighter corners. So you feel the effects of your speed, even though it's not as great as an outdoor roller coaster, you feel the effects of it more because the corners are sharp. Okay, and so people black out on the Mindbender all the time. Okay, because we used to do a trip, okay, where we would go to West Edmonton Mall and people would ride all the rides and stuff like that. We don't unfortunately do it anymore. Okay, and we had people black out on that thing all the time. Okay, funniest one was the person who was screaming all the way up. But that's not even the scary part. They were screaming all the way up, and then when they did the drop, they were screaming, and then the screaming just stopped. And when they came by where you could see them, their head was bobbing all over the place because they were unconscious, which was pretty funny. All right. Yeah, so it's got a lot of high G forces because on those corners you have a lot of kinetic energy. You're moving fairly fast. Okay, you wouldn't notice that near the top. Okay, higher points, you're not going as fast, so you don't notice it nearly as much. Okay, questions on that idea? Okay with that? Yeah. All right, now, the principle of the conservation of mechanical energy tells us, okay, how things are going to work. All right, now, this is one of the coolest things I've ever seen. I know you're looking at this and you're even nerdier than I thought. Okay, but wait for it. Okay, so at the track and field facility in Edmonton at U of A, okay, they have this ramp. It's used for returning shot puts to the throwing area. Okay, now you look at this and you go, what? Anybody could have thought of that. You build a ramp, you put the shot put on it, it'll roll down the ramp and go in. Except that this one works perfectly. If you put a shot put at the top of this ramp, it rolls down the ramp. That's not the exciting part. Okay, and then it rolls along this track. What's acting on it all along this track? Friction. When it gets to the end of the track, it runs out of energy and it stops right before it falls off the end of the track. So it's not like going to the bowling alley, you know, where bowling balls come in and smash people's fingers because they're still moving really fast. Okay, this one is designed so that if you put it here, the amount of work you do to lift it here will be the amount of energy it loses along the length of the track. Now, if you roll it, if you put it at the top and give it a push, then it'll roll off the end because you're doing extra work, giving it some kinetic energy. But if you just put it at the top, okay, the energy is conserved. It's just turned into heat and sound as it rolls along the length of the track. Okay. Now, when I used to coach track and field and I first saw this, I brought the whole team over. Yeah, they all gave me that same look they're giving me right now. Yeah. Okay. Because I'm a nerd and I can live with that. Okay, that's who I am. But okay, they all got the little impromptu physics lesson. And all the other people who are also there give me that same look they're giving me. Okay? But it was really cool because it was like physics working. Okay? Yeah. All right, I get it. I'm still not taking the picture off this problem. Okay. So, applications of this. All the winter sports, okay, that go on kind of in the Winter Olympics that have to do with sledding. Okay, so that would be the bobsled, the luge, and now for people where luge isn't crazy enough, skeleton, okay, which is aptly named because it's luge, but you go down head first instead of feet first. Okay, all of those sports rely on the law of conservation of energy. Okay, you start at the top of this track and you go to the bottom, and by the time you get to the bottom, all of the mechanical energy you had at the top is turned into kinetic energy and you're going really fast. Okay, that's good and bad. In 2010 in Vancouver, they had a problem with the skeleton track. They had a lot of rainfall with freezing temperatures. And the track actually ended up being more slippery than they had designed it to be. And on one of the practice runs, on the first or second corner, one of the athletes went out of the track and was killed. Okay? So they had to very quickly, obviously, like change the track so that that wouldn't happen again. What's the simplest solution? If you're going too fast on this corner, but you still want to make it competitive, what's the simplest solution? No, well, they couldn't change the track.
Wider and taller.
Couldn't change the track.
Wait, like the person's controlling on the sled or just the track?
What could the organizers do? They can't change what the athletes really are doing while they're steering it, and they can't change the design of that corner. Okay, they could try that, but they don't really have a lot of control over that either. It's weather dependent, right? Okay. The reason I have too much energy and I'm going too fast is because I had too much energy up here, right? The energy here and the energy here are equal. So if I want to have less energy, start lower, right? Simple solution. Okay? That's what they ended up doing. They just shortened the track. Now you can't have enough energy at that point to go out of the track. Okay? They just made the track a little bit shorter. Okay? So people wouldn't have enough mechanical energy, kinetic energy on that corner to go out of the corner. Okay? All right. So what we have to get basically out of this is that Yes, energy is conserved. If there are no non-conservative forces like friction, and we would imagine there aren't, okay, the amount of energy is going to be the same. So our mechanical energy stays at 600,000 joules, okay, all the way to the bottom. But what changes is at the top it's all potential, okay, and as we're going down, that potential is converting into kinetic, but the sum is always 600,000. Everybody all right with that idea? Okay, so that's the principle behind all of those winter sports, roller coasters, okay, all of that kind of stuff. They all rely on potential energy being converted into kinetic energy. All right, we're going to talk some more about this tomorrow. Okay, remember you've got a unit exam coming up on the 15th, sorry, 17th, not 15th, 17th for you guys. So make sure you're continuing to prepare for that. Okay, I'm here for help if you need it, so make sure you're popping in during any of my help times. Okay, the unit exam review, okay, is the last pages, obviously, of your workbook, digital workbook. That's what we're looking for. Okay, but I will do a unit exam review, a formal one, probably on Friday. Okay, that's the usual thing when I talk about